Okay. All right, so on Wednesday we went over most of the rest of 2.2. We had one more example left to do, excuse me, because we essentially have to go the opposite direction. So we were talking about finding the derivative graph given an original graph, and now we essentially have to go the opposite way. So we're going to write down kind of the process to do that. We're going to go through one example, because this is not as often asked as the opposite direction that we were talking about on Wednesday. And then we'll move on to 2.3. So if we are given a derivative graph, the first thing we want to do is we want to look at the, should have had this set up already. We want to look at the zeros of the function. Now, oh, excuse you. In the original notes, it says where it touches the x-axis. I'm going to cross that out. I probably shouldn't have included it. Where it touches the x-axis is kind of a point of interest, but not a point of interest enough that it will be helpful. So I'm not going to include it. So specifically, we're going to look for where it crosses the x-axis. Whoa. So we're going to look for where it crosses the x-axis, and at these points, the original function is going to have either a maximum or a minimum. At this point in time, we're not going to know which one. In a few weeks, we'll have some new material under our belts that we would be able to know which one it should be. But at this point in time, we don't really know whether it's going to be a max or a min, as long as it is one or the other. With this second piece of information, we'll be able to figure out which one is the correct option. So sometimes this first piece is enough, but usually more often than not, we will need this second piece of information for this direction. So what you do then is kind of the opposite of what we were doing last time. So we're going to look at where the derivative graph is positive and where it's negative. Because that's going to tell us where the original function is increasing and decreasing respectively. We're using that relationship between the two types of functions that I said was really, really super important. And just like with the opposite direction, in terms of the problems we will, In terms of the problems we will be looking at, 1 and 2 is enough. But if you were to need more information, there's not a lot we can say without being given some more stuff. But if you kind of wanted to know what it should be doing above or below the x-axis, what you could do is you could look at the y value of the derivative, and that would kind of tell you how steep the function should be. Should it be increasing very quickly? Should it be increasing very slowly? That kind of idea. The larger the y value, the steeper the function should be at that point. But again, most of the time we don't need to go into that specific, that much specific information pulling, if you will. My brain isn't working. We don't need to go that deep into it, if you will. So I'll leave this up for like 5 more seconds so y'all can get that down before we do the example. And then we'll go on to section 2.3. So let's go down to this one example of this. And so just like last time, sorry that they're a little blurry, but we'll be able to essentially pull the information we need, even though it's a little blurry. So on Wednesday, we were looking for maxes and mins, but today, because we're given the derivative, the first thing we're told to do is to find the zeros. So we have to find where it crosses the x-axis. Now, technically, it also kind of crosses back here at the very end. That one's not going to be that helpful necessarily because it's so close to the end of the graph. So we're really going to focus on these two because even though it does technically cross the x-axis back there, since it's so close to the end of the graph, it might not be very helpful. So let's just focus on the two that we have there. That should be enough to figure out which one this should be. So let me split that graph up kind of at those places. So we're at about -3 and about 2. So let me go to my answer choices. Now this way is a bit harder to see, I think, especially because people get so used to going the way we were going on Wednesday, that even though this way isn't necessarily any more complicated, you've now got it all mixed up in your brain. So what I'm going to do is I'm going to break up the other graphs at -3 and 2 as well. So, and I know the numbers are super blurry, but -3 is about here, and 2 is about here. -3 and 2. -3 and 2. So now that I've split them up in those places, so the point is that whenever the derivative crosses the x-axis, we want a maximum or a minimum. So let's go over to letter C first. At at those 2 points, if this were the correct graph, I would have to have a maximum or a minimum at both of those points, and neither of that happens at either of those 2 points. Like my max turns out to be over here and my min's over here, and I'm pretty kind of straight across in the middle. So it's definitely not option C. Option B is looking really good. Now option A, I'm going to keep that in the running for now. Technically, this max is too far to the left of where it should be. So you can probably just, not probably, you can just say that that one's out of the running because that one's too far to the left. This one, this minimum here is so close to where it should be that that's kind of like you can't really count that out. But that maximum on the left is a bit too far over. But let's say that you weren't quite sure and you wanted to keep it in the running for a little bit. So then how would you figure it out from there if you're not entirely sure if A is out or not? Well, then we'd have to look at essentially that negative, decreasing, positive, increasing relationship. So if I go back to my derivative graph, I'm going to note that the derivative is negative, kind of in that leftmost piece. And then it's above the x-axis, so it would be positive in that piece. And then kind of in that rightmost section, it goes back to being below the x-axis, so it would go back to being negative. So if I think about my relationship between the derivative and the original function, that means that my original function, since the derivative is negative, my original function would need to be decreasing, and then increasing through this entire piece, and then decreasing. So if I go back to my 2 options that I have left, I want something that's decreasing, increasing, and then decreasing again, which essentially gets me that my only possible option here is B, because my option A essentially goes in the opposite order than I wanted it to. So even if you were not quite sure whether that maximum was enough in the right place, the fact that it essentially has the opposite increasing, decreasing layout, if you will, definitely means that A is not our option, and our answer was B. Does that make sense? Are there any questions on that? And any questions about 2-2 before I move on to 2-3? So we only did this one example of this direction. Again, this direction isn't asked as often as the other direction. It's good to know, of course, but usually, more often than not, we do the other way. But do be careful when you're reading Wiley and make sure you know which graph they're actually giving you to start with. All right, so I'm not seeing any questions, so I will move over to 2.3. Where is it? Here. Come on, there we go. So 2.3 is called Interpretations of the Derivative. Now, half of this material, because there's kind of 2 big pieces of 2.3, the one piece we've already slightly talked about, and that's the interpretation piece. There's another piece that we might actually not get to today, but anyway. So we've already been interpreting derivatives without necessarily knowing that we were interpreting derivatives. But remember that the derivative is equivalent to the instantaneous rate of change, and that the instantaneous rate of change is a slope. So since if we were to then interpret a derivative, we would be interpreting a slope, and we've already been interpreting slopes. And I said a couple of times that it would come back to bite us, and this is the section where it does. So say we have a function y equals f of x. Then the average rate of change, whoops, I always forget to pull the pen up. So the average rate of change is given by some change in y over change in x. So remember that, the average rate of change is essentially a slope, usually written as f of b minus f of a all over b minus a. Another way, why did that move over? Another way to write that would be kind of this change in y over change in x notation. I think I've mentioned this before, but just in case, I don't think I've written it down ever. That little delta, that little triangle symbol, essentially can be thought of as meaning change in. So anyway, so the average rate of change is some change in y over change in x. So if we have a very small change in x value, then essentially the derivative is approximated by that change in y over change in x, which is actually not new information. That's exactly what we went through in 2.1. We were taking the average rate of change for a very small change in x. We were taking two numbers that were obnoxiously close to each other, so their change in x would be small, and using that to approximate the derivative. Now this also implies that if we essentially take that change in x and kind of swing it over to the other side, that we could also write this. This is just an algebraic manipulation of the thing above it. We're taking that change of x and we're essentially swinging it over to the other side. Now, if I think about what that change in x is actually representing, I could say that that's some x2 minus x1, and the change in y is some y2 minus y1. Now run out of space. Go down a little bit. Actually, because I'm running out of space, I'm going to change back to change of x, but I'm going to keep the y2 and y1. If I add the y1 over to the other side, I would get this. Now, you might not know where I'm going with that, but hopefully you understand where I'm getting one line from the next from. So this one, I'm just essentially rewriting the change in y and change in x as to essentially what they mean. And then from here to there, I'm just taking that y1 and adding it over to the other side. Now, what I've essentially done is I've set up kind of the idea that we might not actually get to today. But this idea, the fact that we can kind of algebraically manipulate kind of this average rate of change idea and swing some things over and add some things over and get this, is actually highly important, because essentially it's going to give us a way to estimate a value of the function. But again, I don't think we'll get there today, so I'm going to stop talking about it and I'll just come back to it on Monday when we get there. Because I don't want to spend time talking about it and then have everyone just forget it anyway, which is fine. So the other piece, so that kind of sets us up for kind of the second half of 2.3. But in the first half, we got to talk about this thing called Leibniz notation. So history. Calculus was essentially created by two guys at the same time, but they didn't know the other person was creating calculus. So there was Newton and then there was Leibniz, and they pretty much both created calculus, both with their own separate notations. And everyone usually uses the Newtonian. So what we've been writing, this f prime of x, is Newtonian. But there's this also Leibniz notation for the other guy who was creating calculus at the same time. And he wrote his derivatives like this, dy over dx. Now, why the heck would we care about which one we use? Well, first of all, before I get there, if I were to read this, I would actually read this as the derivative of y with respect to x. That's how I would read that. Well, you might hear me also say dy over dx, but formally it's read as the derivative of y with respect to x. Now this notation, why the heck are we using it, is especially helpful in determining the units of the derivative. And that's kind of what we're going to use it for, is to determine the units of the derivative. Because if I just say f prime of x, you might not know exactly how the units are going to go. But the nice thing about the dy over dx notation is essentially this idea. The units of the derivative of a function are going to be the units of the dependent variable. And I'll write y in parentheses, because that's usually what people think of when, people usually think in terms of y's and x, and y would be the dependent, divided by the units of the independent. which would be x if you have an x. In other words, say we had some dA over dB as our derivative. The units are going to be the units of A divided by the units of B. So that's like the super nice thing about Leibniz notation, is that the units just kind of fall out because you have dA give you the units of A, and then dB give you the units of B, and it just kind of mirrors itself. Whereas if I just say f prime of A, you might not exactly know this setup for the units. So Leibniz notation is often used a lot when we want to try to pull out the units. And in a general calculus course, Leibniz notation is also needed much more often for some topics that we don't cover in this class. So it's not just necessarily this notation that is just used for units, it's also used for other pieces of calculus that we just don't cover. Anyway, also, if the derivative of a function is not changing rapidly, I'll try to explain that in a second, what I mean by changing rapidly. So if it is not changing rapidly near a point, then the derivative is approximately equal to the change in the function when the independent variable increases by 1. And I'll try to talk about that more in just a second too. So I'll pause for a second for y'all to get those down before I babble about this piece a little bit more. So what the heck do I mean by changing rapidly? Say I have a function that looks like this, and then one that looks like that. No. Sure. And say I want to look at, let me get a new color for this. Say I want to do tangent lines on here. And say I want to take the tangent line right here. So let me draw that to the best of my ability. And the tangent line, say, right here. Okay. So I have some function, and then I have a tangent line. Well, if I look at the one on the left, say I go over, kind of one in either direction. Not even necessarily, let's just go in one direction. If we go over one in that direction, notice that that tangent line is still obnoxiously close to that function. It's still pretty close. And even if I go kind of over another one, that's still, that's not too far away. It's not perfect. It's not super, super close, but it wouldn't give me a bad approximation if I were to know what the value of the tangent line would be at that point. But then say I pop over this one on the right, if I go over, one, well, that's not too bad. But then if I go over one more, kind of a wishy-washy in terms of what going over one means, then I start getting really far away from the function, between the tangent line and the actual function. So that's what I kind of mean by changing rapidly. So is the function increasing kind of very steeply or decreasing very steeply? Or is it increasing or decreasing very slowly? And if it's at a kind of slow pace, if you will, then what's going to happen is the tangent line is actually going to end up being a pretty decent approximation for that function, and a pretty decent kind of interval. That tangent line doesn't match the graph perfectly, but it does give me a pretty decent approximation of where my function would be if I were to just know what y value the tangent line had. Whereas with my one on the right, it could be pretty good really close by, but the farther away I get, it starts to not be a really good approximation at all because I have this really big space between the tangent line and the function. So the point is that sometimes we're also able to say, it's kind of like back when we first presented the idea of interpreting a slope. Remember, there was kind of the two ways that we wrote it. There was the rate way and then the step way, where we were kind of looking at if we go over one, how much does the slope take us up? And we kind of had that the little steps for the slope. that's kind of what this sentence is kind of saying, is that we can approximate the derivative to essentially be, if I go over 1, how much do I go up by? That's essentially what that's saying, is that we can kind of use that idea of kind of the step of the slope, if you will, to estimate the derivative. So this idea is also going to come back. Again, I don't think we're going to get to it on Monday. We're kind of building stuff up for what we'll have to hit on Monday. But going back to Leibniz notation really quick. To specify an evaluated value in Leibniz notation, what I mean by that is, say I wanted to say something like f prime of 2. Now, the bad thing about Leibniz notation is writing something like that is tedious. More tedious than just saying f prime of 2. Because the way you would do this in Leibniz notation is you'd have to say dy over dx, then you have this little line, and then you say x equals 2. So it doesn't look quite as nice in Leibniz notation, but that's how you'd write it. So you will want to be, and again, while we don't necessarily need to use one over the other, you do want to be comfortable seeing both forms. Like if I were to write this down, you'd need to know what it means. So don't think that you can necessarily just focus on Newtonian, even though that's used way more often and you get to kind of choose which one makes you happier. You do need to be able to recognize both. So now the next big piece we're going to talk about, which again, we've kind of gone over already, but we're going to finally write down in formality, is how we're going to be able to interpret these derivatives. So again, this is kind of, we've already done this. We've been interpreting slopes, and we kind of had a rate way, and we kind of had a step way, if you will. And that was, you know, that step idea that I was just talking about. But let's write all of this down in, you know, formality. So in both cases, you must include 3 things. And my pen stopped working. 3 things in your interpretation. Now, this is a choice. You get to choose which one of these 2 makes you happier. But kind of like Leibniz notation versus Newtonian, you do have to be able to recognize both, because I believe on Wiley, sometimes they'll, you know, it'll be a drop-down box and you just have to like fill in the sentence. So you kind of need to know the structure of both so that you can answer it, even if it's written in a step way, but you prefer the rate way. But anyway, so there's kind of 3 things that you always need to write down when you're doing your interpretation. The first thing you do is you have to state the starting x value. And this is actually the same in both, so let me just write it for both really quick. So state the starting x value. And we'll do an example of this in a second, but I just want to write down this process first. So in both cases, you state the starting x value. So say we were saying something like, we had like f prime of 2007 equals 15, and this is a change in population, let's say in million per year. You don't have to write this piece down. I just want to try to talk some things out as I'm writing this down, and this is kind of the thing I'm going to be phrasing it as. So in this case, well, I guess let me just try to jam it in here really quick. So we'd have to say like after 2007, if I was doing this kind of example down here. And you would have to do that in either case. You'd have to essentially tell them where you're starting at. The next thing you do for the rate thing is you essentially state the direction. What I mean by direction is increasing or decreasing. So the direction of the y value using context. So let me even say y value context to be clear. So what I'd mean by that in this kind of tiny example I have down here, we'd have to say that the population is increasing. Specifically increasing because the value of the derivative was positive. So you kind of state the direction that the y value is changing in, and then you state the derivative value. And I'm going to say with rate units. And that's because there's a difference between the two, what type of units you use. For this one, you essentially use the units of the actual derivative value. So we'd say something like 15 million people per year. If we're going with that kind of tiny example that I just shoved in at the bottom there. And kind of just stating those three things would get you the interpretation. So I'll pause really quick so people can get that down before I write down the other one. Well, let me just write after 2007 because that's the same thing as before. So the second thing you want to write down for the step way is, so you always start with stating the starting x value first, but then what you do here is you're going to essentially, you're going to state that you add one more x, and x being the context of the x value in the problem. So in this case, we would say essentially adding another year, or sometimes you might use each additional year. So you essentially tell them that you're adding one to the x value. And then you're going to state how much the y value changes. And here we just use the units of the y. Let me try to. So in this case, it would essentially be, so if we add another year, the population, the y value increases by 15 million people. It's no longer people per year, it's just the y value units. So anyway, that was a lot to say, something that we've somewhat already gone over, but just to kind of write it out in full formality, because you're going to want to do this a lot in 2.3. So this is just something you can refer back to if you're having trouble kind of putting it in the right format. I'll have this up for a couple more seconds before we scroll down to the example. And again, you get to pick whichever one of these two types makes you happier, but you will want to kind of be able to recognize both formats. So let's look. We can try to keep kind of that last bit in there for a little bit. I'll need to scroll down in a second, but just that last piece, try to squeeze in there. So say we have Q equals F of P gives the number. Now this one, the units get a little tedious, but I actually think that's actually helpful because it sounds so weird, but the setup kind of just lays it out for us. So if we have Q equals F of P gives the number of thousands of tons of zinc produced when the price P dollars per ton, if my pen will work. So kind of circling the units we're going to be using. Then what are the units of the meaning of, let me just rewrite this because A, I kind of put a slash through it, and B, P's and Q's are somewhat looking like each other. And I should really start putting zeros before my decimal numbers. So we have dQ over dP at P equals 900 being equal to 0.2. So we want to interpret this. Well, first thing is we want the units. Let's do that first. Well, let's look at the fact that we've got this Leibniz notation. So if we've got that Leibniz notation, then that's going to tell us that the units are going to be the units of Q, which are thousands of tons of zinc. Again, units here are a tiny bit tedious, but, and then the units of P were dollars per ton. So those are going to be our units of our derivative. A bit weird units, but those would be our units. Now for this example, and pretty much this example only, I'm going to go through both of them just so you can kind of see how they get laid out in both cases. And then from here on out, I'll just choose one over the other in each case, unless someone specifically asks to see the other form after I've written down whatever I've written down. Anyway, so I want to write down the right way for this. Always need to start with a starting quote unquote X value here, which would be our P value of 900. So we'd have to say essentially after $900 per ton. So this is essentially our step one. And then we say how much we essentially tell them whether the Y values are increasing or decreasing, and we're going to use our units as well. So that's going to be the Q values. And since our derivative value is positive, that's going to be increasing. So we're going to say the amount of zinc produced is increasing by, but that's our second step, so I'll pause for a second. That's kind of our step two. It's telling us where we're increasing or decreasing. And then we state our derivative value, so increasing by 0.2, and we use the units of the derivative. So the units of the derivative are kind of long, but here we go. So 0.2 thousands of tons of zinc per dollars per ton. And that last piece is essentially the step 3 of the rate interpretation. And so I'll pause for a second before I do the step 1. Again, I'm just going to do both for this first example. So say we wanted to do the step way, we start similarly after $900 per ton. And then we tell them that we're going to increase the quote unquote X value. So we're going to increase P by 1. So I would say, I would phrase it, I usually phrase it as after $900 per ton, increasing the price by $1 per ton. It's always increasing X. So the thing that changes depending on the slope value would not be this increasing the price. That change in X value is always increasing. So increasing the price by $1 per ton is essentially that kind of second step in the step way. So increasing the price by $1 per ton increases the amount of zinc by 0.2, and here it's just thousands of tons of zinc. So it's no longer that entire kind of derivative unit, it's just the units of the Q value. So again, whichever one of these two types makes you happier, you just have to do one of them. questions, concerns before I go to the next one? We'll do 2 more and we'll be done. All righty. Let me try to leave some of that in there. Can I leave all of it in there? Yeah. Okay, cool. So the cost in dollars of building a house that is A square feet in area is given by the function C equals f of A. What are the units and practical interpretation of the function f prime of A? So here we're not given any values, so it's going to make our interpretation, I don't want to say harder because it's not what I'm going for, but the interpretations that we just did very much rely on having values. So here our interpretation is going to be a bit more generic. But let's focus on the units first. Let me actually pull out our Leibniz notation because as it stands, f prime of A, maybe I have no idea what the heck that's supposed to look like in terms of units. Let me think about what the Leibniz notation would be here. Well, it's going to be whatever our y value is over our x value. So here, our c value is essentially acting as our y. So our Leibniz notation would look like dc over dA. Once I have it written like that, kind of makes the units easy to figure out because what are the units of C? The units of C are dollars. What are the units of A? Units of A are square feet. So we have dollars per square feet.
Can you scroll up for just a second?
Yeah. Like all the way up to the other page, all the way up?
No, just to example 1.
So, I'm at units, dollars per
Yeah,
square
you're good. You're good. Thank you.
Thank you. So now I want to interpret this, and again, our interpretation is going to be a bit more generic here because we don't have the exact amounts to tell them where we're starting at or how much we're increasing by. But if you think about, again, what the slope is kind of telling you in general, it's telling you if you increase by so many x values, you're increasing by so many y values. So what are we looking at here? We're looking at expanding a house. We're looking at increasing the amount of square feet, which is going to then increase the amount of dollars we're paying. So the interpretation, if we think about it in terms of like an increase in square feet would give an increase in price, we would essentially be giving the cost to build 1 more square foot. If we kind of focus on it as that change in one idea. So the cost to build 1 more square foot on a building that is a square feet. You could also think about it, if you wanted to think about it, this is kind of more the step way. If you wanted to think about it more in terms of the rate way, this would be essentially the cost per square foot. Which is exactly what this thing is saying up here, just in a bit more words. Questions, concerns about that one before I go to the last one we'll cover for today? All right, so going down to this one. Let me try to leave some of that in there before I scroll all the way down. So let's see, we have the time L in hours that a drug stays in a person's system is a function of the quantity administered, Q in milligrams, so L equals F of Q. We want to interpret the statement F of 10 equals 6 and give the units on the 10 and the 6. Now be careful here because this isn't a derivative value. This is a regular old function value. We don't have a prime here. We just have regular old F of 10, not F prime of 10. But let's think about what both of these values would be. Well, that 10 is a Q value, so that would be in milligrams. And this 6 is essentially an L value, so that would be in hours. So essentially just slap that into the context, if you will. 10 milligrams, 6 hours. What is this talking about? It's talking about how long it stays in a person's system. So essentially, if 10 milligrams of the drug is administered, it stays in their system for 6 hours. So just regular old function, no rate, no changing, increasing, decreasing, none of that. Just telling us that 10 milligrams stays in the system for 6 hours. Okay, last two pieces of this one. No, there. So write the derivative of the function Leibniz notation if f prime of 10 equals 0.5. I really should put zeros there. What are the units of the 0.5? So we don't want to interpret it yet. That's going to be part 3, but we do want to state the units. So first thing, Leibniz. I always want to put a T in there. I feel like there is a T in there. I don't remember. It's a name. But anyway, Leibniz notation. So if we have L equals f of q, then our Leibniz notation is going to turn out to be dl over dq. And so what would the units of that be? Well, what are the units of L? The units of L are in hours. What are the units of Q? Well, that's in milligrams. So hours per milligram are going to be the units of the derivative value. So that 0.5 has units hours per milligram. And then we want to interpret it. Now I'm just going to interpret it one way. I will write the other way and I'll post that on Blackboard. And well, you can stick around at the very end if you want to see me write it out. But I'm just going to go with the right way officially, and then we'll end. But I'll have the step way written on the notes if you want to look at it later. So if I want to interpret this in the right way, well, again, first thing you always got to do, tell them where you start. So we started with 10 milligrams of the drug. So essentially after administering 10 milligrams of the drug, state the starting X value, tell them how the Y value is increasing or decreasing, and refer to the context. So since we're talking about how long the drug stays in a person's system and the value of the derivative is positive, we'll say something like after administering 10 milligrams of the drug, the amount of time the drug stays in their system kind of that Y value context is increasing by, and then we finally give them the actual value of the derivative and use our derivative units. So by 0.5 hours per milligram. Now, I'm not a huge stickler for making it sound like decent English. I know some of these I might phrase very poorly because I'm a math person. I don't really care about English. But anyway, as long as you get the point across of the fact that you're starting at a certain value and you're either increasing or decreasing depending on the sign of the derivative by the derivative value, as long as you get that point across, I'm not a big stickler for how it's phrased per se, but it does need to include kind of those three things. So those three things that we were talking about earlier, those three things always need to appear, but exactly how you write it, as long as it gets the point across. I'm not a huge stickler for the phrasing. But we're going to end there 5 minutes early. Again, I'm going to stick around and I'm going to write the other way down so that it gets on the notes the step way in case people like to use that way. If you want to stick around and watch me write it, feel free. If you don't, feel free to leave. Have a great weekend. I'll say one last thing really quick. Your Wiley homework. So there's this one last topic that we haven't hit yet. And I just triple checked before I came to this class. There's only 3 questions on Wiley that you can't answer yet. So like, well, yes, and I'm still super sorry that we didn't get through all of it. We were supposed to get all of 2-3 today, but it didn't happen, obviously. But you can do all of the homework up until the last 3 questions. And I think, just having 3 that have to get done on Monday isn't the worst thing in existence. So the large majority of your homework you can already do based off of what we've covered so far. Those last 3, you just might have to wait until after we talk about stuff on Monday. But anyway, I will write this down. Feel free to leave and have a great weekend. This one would be, if you have any questions, also feel free to stick around for a little bit and ask me questions. So after administering 10 milligrams of the drug, increasing no, how do you spell? Increase, oh my God. Increasing by 1 milligram. How do I phrase this? Increasing by 1 milligram. Oh, I should phrase it like that instead. Administering 1 more milligram. Will cause the drug to stay in their body an extra half hour. So stick around to see that other way. There's a ton of ways you could phrase that. Because it sounded slightly better this way. But as long as you get the point across, starting at 10, adding 1 more, what does your Y value increase by? So if you have any questions, let me know. Otherwise, have a great day. I'm going to stop the recording.